In a previous video, we gave an interpretation of the flux of a vector field across a curve, right? And we said, imagine a uniform layer of fluid, right, of constant density moving across the XY plane, all right, thin enough to consider to be two-dimensional, all right? And so similar to that video, I'll link to it in the description so you could take a look at that later. Here's a little situation it illustrates the point. Here's my curve C. The vector field represents the velocity of a fluid at any point in that field. What's the net amount of fluid that crosses or flows across the curve C? And the way that we explained it in that previous video was we said, I will take a little arc of the curve. Okay, here's a magnification of it right here. Call the length of that arc ds. Okay, notice the green vector here. Remember that one? That was the unit normal vector to the curve. Okay. Also notice I have a blue vector. Here's one of the field vectors right here that actually emanates from the curve. Okay. And we say that the amount of fluid that crosses that little arc right there is approximately equal to the area of this parallelogram right here. Okay. Well, again, the area of a parallelogram is the height of the parallelogram times its base. Now the base is just ds. We just have to figure the height, and we can get that. This distance right here, a little bit of right triangle trigonometry, right? We've seen this before. This is just simply the magnitude of the vector f times the cosine of theta. Okay, this scalar quantity right here, the scalar projection of the blue vector onto the green one. Okay, and so therefore the area of the parallelogram is approximately equal to, well, it's not a perfect parallelogram because of the bottom right there, but it's thin enough. It's a differential element. It's practically a parallelogram, right? Is going to be the height times the base. Okay. And then what we did was we multiplied that expression by a clever expression of 1, the length of the unit vector. Okay. And of course, by the definition of dot product, I can replace those three factors then with this. Okay. And so, of course, we imagine the curve is made up of an infinite amount of those tiny arcs. And so we sum up all of those little pieces. And so we say the total flux of the vector field is equal to the line integral along the curve or over the curve. Okay. Now we also saw that that was equal to the expression or the line integral negative g of xy dx plus f of x and y dy. Okay. Now, what about 3 dimensions? Okay. Same concept, a vector field, but what about 3 dimensions? Well, again, consider this. This time, the fluid is moving through a surface, 3-dimensional surface. And our parallelogram, our 2-dimensional parallelogram is now a 3-dimensional, looks like a parallelepiped, doesn't it? It looks like a column, okay? And what we want to know is what's the net amount of fluid that crosses through this surface right here? All right, here's the vector field, or portion of it. Here's a little patch on the surface, okay? Now remember, in 2 dimensions, we used a little arc of the curve, okay? And the amount of fluid that passed through it was approximately a parallelogram. Well, this time in 3 dimensions, instead of a little arc, we have a little patch on the surface. We'll call it ds, and that's a capital S, gang, because remember, we use capital S for surface. So the differential element of surface would be ds. Now that's a copy of the little patch right here. What's the amount of fluid that crosses through it would be this column right here. The situation is essentially the same, it's just 3-dimensional. Here is my normal vector to the surface. Okay. Notice I have one of the field vectors attached to the surface right here. And to find the amount of fluid passing through this little patch right here, I need to find the height of the column and multiply it by the base of the column. Well, again, the base of the column is ds, that little differential element of surface area, we call it. Okay. All right, so let's see. If we reason the same way we did before, the scalar projection of the red vector onto the green one would be this, okay? And so therefore, the volume of that column would be equal to its height times the base. Okay, very similar to what we did in 2 dimensions. And then I'm going to multiply it again by our clever expression of 1. Okay, and I can replace these 3 factors with the dot product of f with the unit vector. Okay, again, once again, very similar to what we just showed in 2 dimensions. Okay. Now, of course, we imagine that surface made up of an infinite amount of those tiny little patches. So what's the total or net amount of fluid that crosses the surface? Well, that's going to equal this. Okay. We call that the flux integral of the vector field F. Okay. The flux vector, or the flux integral rather, the vector field through the surface S. It's the and represents the net amount of fluid. We're talking about a volume here, gang, right? Because we're 3 dimensions now. Talking about the volume of fluid that passes the net amount, of course, that passes through that surface per unit of time is what it is. I will point out though, again, and we mentioned in yet another video, right, that this is a form of a surface integral. The general form of a surface integral, we said then in that video, looked like this. In this case, the integrand is the dot product of 2 vectors. So you essentially what you do, guys, when you simplify, when you solve a surface integral, a flux integral like this, you do it essentially the same way you did these integrals. In other words, you put them in parametric form. Okay. Now you don't have to. You can keep them in rectangular form. We've seen examples of that as well in the previous video. But I just wanted to give you a short little video and give you an interpretation of what it means for the vector field to cross a surface. Okay. Surface integrals of vector fields.